Hello everyone, I'm Igor. I'm working in Chatham Financial. I've joined about 1 year ago, and today I'm gonna be talking about mutation testing. The first question, how many of you have heard about the mutation testing? Okay. This presentation is split into two parts. In the first part, I'm gonna be talking about mutation testing. I will show you a short demo of the Striker. The Striker is the framework that is used for mutation testing. And let's roll. So first, we have to answer the question, why do we test our code? The first obvious answer is that to ensure that the code that we've written works properly, that every functionality that we've implemented is covered by the tests. Actually, I would bet that every one of you have written a code that has bugs. And that's okay, actually, because people make mistakes. That's why we are writing a test for them. The other answer could be that we want to have regression based for the future development, so that every time we made a change into our code, we want to have some mechanism that would check for us whether we broke something or not. But for this presentation, I'm going to focus on the first answer, that we want to ensure that our code works properly. So having in mind that we do not believe in our coding skills, because that's why we are writing a test for our code. There is a question that comes up, that should we believe that the tests that we've written are robust enough? Should we believe that the tests we've written are testing the whole functionality that the code implements? And I think the question is that we shouldn't, of course. So in order to measure the robustness of our test suite, people invented some metrics. One of the metrics is the code coverage index. So it basically, during running the test suite, we counting the number of the lines of the code that has been invoked during the test run, and then computing the ratio between the number of lines that were invoked during the test run and the overall number of lines in the code. But this actually doesn't tell us much about the robustness of our tests. I will explain it later. And the other thing that we can use to measure the robustness of our test suite is the mutation testing. So what is it all about? The prerequisites of the mutation testing is that we have to have a code base, and we have to have a test suite that is going to test our code base. In the first step, we just run the test suite without any changes applied into the code base. And here the first run has to pass, just because if it doesn't, we cannot make any reasonings about the future results of the mutations. So when the first test run passes, then we can introduce a tiny change into our code base. And this small code change is called a mutation. And it is very important that in one point in the time, we are making only the one change in the code base, and only to the production code, not to the test code. Oh, it's not mine, because I have the same rainbow. Yeah, and after making a change into our code, then we are running the test suite again. And there are a few possible outcomes of this testing. They're either all the tests pass, or there is at least one test that fails. And of course, if there is after making a change into our code and running the test suite, there is a test that fails, it means that the functionality that has been changed by the mutation is covered by the test. So let's go on. So these are some basic examples of the mutation testing. So here we have a code that for loop that goes from 0 to 99, and after the mutation, we're changing the I is less than 100 into I is greater than 100. Another one is that we're changing the logical AND into logical OR. So this one are basic examples. I will show more mutations later on. So how do we interpret the results of the mutation testing? So after making a change into our code, there are two possible outcomes. So all the tests pass. It means that even though we made a change into our code, we changed the functionality of our code, the logic, all the tests pass, then it means that we don't have a test for this particular functionality. So this kind of mutations are called the mutations that survived. And in this case, actually, we have also two possible ways on interpreting this result. Either this code that has been changed is not used, or we do not have a test for this functionality. So here comes your coding skills into the play, and you have to dig through the code and judge whether this is that code that you can trash, or this code is not covered by any test, and you have to write a test for it. The other outcome of the test could be that there is at least one test that failed. It means that after making a change into our code, so we changed the functionality, there is a test that failed. So it means that we have this functionality covered by the test. And it's great, actually. The more killed mutants, the better. The more killed mutants, the better, actually. And the third group of the mutants are the incompetent mutants. It means that this mutant, by making a change into our code, the change that this mutant injects into the code results in either crash or segfault, or, for example, in that the test runs forever. This kind of mutants we want to actually filter out because they do not provide us any meaningful information, because the code that they introduce just doesn't work. So yeah, the goal is to kill them all. So now let's take a look at the code coverage and mutation testing and the differences between that. So the code coverage answers the question that was the line executed. So the answer whether the line was executed or not doesn't tell us much about the robustness of our test suite, because it is very easy, for example, if we have a function that we want to test, it is very easy to write a test that has 100% code coverage, but it doesn't test anything, actually. So the example of this test is just to invoke this function and do not make any assertions. And assuming that in this function we don't have any branches, it means that the function is gonna be executed, the whole lines of the function is gonna be invoked, and then we have 100% code coverage, but we are not testing anything, actually. And the question that that mutation testing answers is that was the functionality verified. So by making a change into our code, making an arbitrary change into our code, we're changing its logic. And then if we know that there exists at least one test that failed, it means that we have at least one test that tests this exact functionality. And it is much more meaningful information. And it actually tells us whether our tests are robust or not. Yeah, wait a second. So far I showed you a few examples of the mutations, and those are other examples, like we can replace the addition with the subtraction, the multiplication with the division. We can change logic operators. We can change pre-incrementation to post-incrementation, or continue to break some. We can introduce some changes for Boolean literals or numerical literals or string literals. So there are a lot of mutations. Those mutations exist for every language actually. Whoa. But with the mutation testing, there are some problem with the mutation testing. One of the problem is that it is a very time-consuming process. So if we have, the execution time of the mutation testing is equal to number of mutants that are we able to inject into our code multiplied by the test suite execution time. It's because we are making for every mutant, we are making the change into the code, and then we run a test, and we are iterating through for all of the mutants. So, for example, if we have 300 of mutants, and the test suite execution time is equal to 5 seconds, we have about, or exactly, 25 minutes. So it's pretty big amount of time, because especially when you have a mutation testing embedded into your build pipeline. So every time you make a merge request, you have to wait additional 25 minutes for getting an answer whether your merge request is okay or not, whether you can merge your merge request or not. So it significantly slows down your development process. So there are a few solutions for this problem. So fortunately, the mutation testing is very easy to be parallelized. So imagine that you have 100 cores, and then you're able to run 100 test suite for 100 mutants in parallel. It significantly speeds up the whole process. Also, you can write the fast tests. And the other solution is to buy the more powerful machine. Yeah, that's gonna speed up the whole process. So from my experience that I had in Chatham, we had a project that, as it grown, the mutation testing lasted for, I don't know, 45 minutes. So it was very hard to work with this. And also the mutation testing, we have mutation testing embedded into our build pipeline. So this significantly slowed down our development process. So we agreed not to run the mutation testing for every merge request, and just because our local machines are more powerful than those that we are using for our build agents, we just agreed to run the mutation testing locally, and only run the mutation testing after the merge request is merged. So that we have kind of automatization of the mutation testing, and we gather the statistics of it. The other problem of the mutation testing is the existence of incompetent mutants. So, as I said before, there are few groups of incompetent mutants. The one group is that after making a change by the mutation, it results in that running the test suite crash or segfaults. But this group is actually very easy to be detected. We just can introduce a change into our code, run the test suite, and we will get the immediate or almost immediate response, whether the test suite failed or crashed or whatever. But there is also another group of incompetent mutants that are more tricky to be detected. So in order to these kind of mutants are that they causes the test suite to run forever. So here's an example of this kind of mutant. So we are changing we have the while loop that runs forever, but it has the break condition. And by mutating this code, we are replacing the break with the continue. And the second snippet, the second while loop runs forever. So it is actually a very hard problem. It's equivalent to the halting problem. If you never heard about the halting problem, it states given a program and the argument for this program, we want to answer yes if and only if this program is going to stop, or answer no if and only if the program is going to run forever. So in 1936, Alan Turing proved that the algorithm that solves this problem cannot exist. And if you want to know more about the halting problem, I strongly encourage you to Google that, or just ask me after the presentation, but now we don't have a time. So, since there is no algorithm that solves that problem, there is no algorithm that will help us to detect this kind of mutants, then we have to come up with some heuristics that would help to filter out this mutant, to detect this incompetent mutant. So the one heuristic is that we can run the test suite against the code that hasn't been changed and measure the time of this run. And then just for every mutant give twice as much time as we needed before. And if the mutant exceeds this time, then we can mark this mutant as incompetent and just throw it away. Because as I said before, incompetent mutants does not provide us any meaningful information. So yes, so far, so this was about the mutation testing in general, and now I'm gonna show you quickly about a Striker. Striker is the framework for mutation testing. It supports JavaScript, C#, and Scala. Unfortunately for C#, it is the only tool that supports .NET Framework, and also it is in the beta version. But I've seen that there is a lot of work happening in order to make the Striker production ready or or version 1, or yep. So let's take a look for a second on the supported mutation by the striker for C#, of course. Whoa, it's not the link. It's not the right link. So yeah, this is the main page of the striker, but I'm sorry, but I have to open it again. Okay. So the striker supports arithmetic operators like replacing addition with the subtraction, equality operators, logical operators, Boolean literals, assignment statements, unary operations, update operators, like, yep, as you can see. And what's the best about the striker is that it supports linQ methods. It's actually a great feature. Also supports the string literals, as you can see. Also, the striker has a pretty nice implementation that it applies all of the mutations at once into the code base, and it compiles the code on the project only once. So it significantly improves the execution time of the mutation testing, because we do not have to compile the code for every mutant. And how is it achieved? So here we can see that is it okay? Ish. So the striker actually put all the mutations into one at once, just because it has something like control of the mutations. And whenever the mutation, for example, 81 is active, then it replaces the initial test run started with the empty string, for example. This line before looked like here, like this one. Oh my, no. Like this one. Okay, so let's quickly run the mutation testing for some project. So in order to run the mutation testing, the striker actually for a C# project, the only thing you have to do is to install the tool that it's named striker. So .NET tool install -g striker, and that's all. And then you have to for your project, oh my god. How is the timing?
5 minutes.
Okay. Okay, so we will run the striker for the striker project, and I hope it. Yeah.